wanted to talk about mechanical failure, Chapter 8, probably the most depressing chapter, but also some of the most fun testing that gets to be done in material science and engineering. And so what we're going to talk about today is how do the cracks that lead to the failure form, how is the fracture resistance quantified for a material, and how do the fracture resistances of different materials compare, and then how do we estimate what stresses are going to cause a fracture, and then how does temperature affect it. And so here we can see some various failures. To the left you can see this very depressing picture of a ship that just completely broke in half. Here's a picture of a computer chip that failed due to thermal loading, and then here's a picture of a hip implant. Of course, meshing apart with the body is oftentimes one of the more challenging engineering problems that can face material scientists, tribologists, and other people that work in this field. So first let's talk about the two mechanisms to fracture. There's ductile fracture, where you have significant plastic deformation before the fracture occurs, and there's brittle fracture, which is little or no plastic deformation and can be quite catastrophic and sudden. So, of course, if you look at what the parts look like after they've fractured, let's say, for example, that you've performed a tensile test on the material, then for a very ductile material, at the break point it's been drawn to a very narrow point. There's a lot of necking, and it forms a sharp point like you see here. If you have a moderately ductile material, like some metals, then you see a little bit of necking and then a fracture across the center. And then for a brittle material, it doesn't neck at all. The nice thing about ductile materials is that you have warning usually before fracture occurs. You can see the necking start to form, the part starts to give, there's more time. Brittle fracture is so sudden and so catastrophic that it's not very desirable. So here's some examples of some images of ductile and brittle failure. This pipe has one large deformation. It's split along the way. This one basically exploded, okay? And it's got in many pieces, sharp deformations, shards flying out, mass hysteria. So you can see why ductile fracture would be preferred over brittle. In moderately ductile fracture, and this would occur in tensile testing of some of the materials that we showed the other day, what happens is you see the neck start to form. And then before the material will fracture, what happens is that there's little voids that form within the material that usually begin to form at flaws that are already existing inside the material. So those voids form, and then eventually they coalesce into sort of an internal crack. And then the part starts to shear at the surface, and then you have your fracture. If you look at a lot of parts that have been put through a tensile stress test, you'll see that there's these 45-degree angles at the edge of the stresses, or at the edge of the breaks, and that of course comes from an earlier chapter where we talked about the resolved shear stress and how 45 degrees is the best angle for that to happen at. So that's why you see that particular structure. If you were to examine the fracture surface, which we'll do in a lab coming up pretty soon, then you can often see that there's sites that served as the nucleation or growth sites for these voids, and they occur at these defects. You can see here in this particular part there were particles that started the voids. And then here you can see what's a pretty typical looking cross section for a metal that's been put through a tensile stress, and it's called that cup and cone structure. Here is the cup part is shown in this image. So here's the cup and cone fracture surface, like I was talking about, and this is what it would look like to the naked eye. Whereas if you put something in there that is more brittle, it just looks straight across almost like that. And that's, of course, that sudden catastrophic failure with no necking. If you have a part sometimes you can track back looking at the wear patterns to indicate where the failure originated. You'll get these wear patterns, and the V will form at the site of the flaw that caused the fracture, that started the crack propagation and the breakage. So you can see that happen in a lot of parts. Now sometimes if you have certain materials, hang on just a second.